them by today. So first, we have our network architecture and assumptions, the same as like everyone has, I think. So our objective is the K out of N.
You can go through all your slides. You don't need to go too quickly.
What?
You don't need to rush through. You can go slide by slide.
Okay. I don't know why it's like doing it by itself. Okay. So we have our every node for the our sessions list. Every node is attached to one router. Every link has the same characteristics, so we're trying to get a hop cost of 1 and the MTU of 1500 bytes. We're trying to have the smallest maximum number of nodes, so we're going to try 50. Our packets are going to be delivered to K out of N destinations, and there's going to be about 50 to 100 nodes in total and 256 hosts in the network. So this is our architecture design diagram. So we have the host here, host 1, 2, and 3. We have our routers, our host 3 and 2 are our receivers. Host 1 is a sender. So this darkened line is the optimal multicast path flow. And this router is where the copying and forwarding would occur. And then this is branched out to these routers where goes to 4 to 5, 6, goes to host 4, and then from 5 it goes to 7 through 11, and here down here 8 and 12, so host 5 and 6 for a K value of 2. So we have about 9 nodes, and the link cost here would be 1. For our concept, we're trying to do it so that we run Dijkstra's algorithm like to the sender's router. So when the algorithm begins to converge, we would select the first K hosts that are connected to the routers closest directly to the sender. In order to find the nearest K host, we were trying to implement a centralized mapping server. So like a lot of companies or organizations where a client sends the request to their server for something, they get a response from their server. And so for the router that we had, router 3 here, for this copying and forwarding, it's going to do this process when the distribution tree has branches attached to it. So our routing algorithm we're still trying to figure this out exactly for what number of K, like whatever K values we're trying to use. So for K equals 1, we have like a unicast packet, and then it would directly forward it to the next hop. And then for the rest of the K values, we have like different instructions for that. So for our centralized mapping server concept, this would be our table. So router 1 through 6 is listed here, our connected host numbers, and then the destination. So in order to find the best K host by destination, we have a routing table here, router 2. So here, in order to get like the least cost, we do router 1, which chooses router 1 from the mapping table, and router 3, which chooses router 3 here from the mapping table. So router 1 would be the second least cost, and router 3 would be the first. And then we have the multicast distribution tree, we're going to use a minimum cost tree. So we're going to use the minimum Steiner tree, which uses a weighted graph, an undirected weighted graph to span to different nodes. So we are trying to use this algorithm, the KMV algorithm, for this tree so that we can have like the nearest optimal solution. So this algorithm basically like computes trees that have about like 5% higher costs than the cost for the minimal Steiner tree. So this would make it the most optimal solution. So this is just explaining how it works. So it begins at a graph and creates the graph, and then a spanning tree is created from that graph. So we'll call that like tree 1 or T1. So from the spanning tree, the edges are replaced by the shortest paths, which give another graph. So then that would be the next graph, and then we would construct another minimal spanning tree, so there would be tree 2. And then the branches in tree 2 that have no nodes are stopped, or like they're pruned and removed after that's done. So in order to make sure that we have like a checking system, we use the automatic repeat request stop. So it requires a stop and waits for the protocol in order to get the sender to receive an acknowledgement from the receiver that confirms that he's gotten the packet before he sends another one. So along with this, we're going to have like a timer that's required. So in the event that there's a timeout, we don't want the system to just like stop sending or receiving packets.